coroutine in Kotlin is essentially a lightweight thread. Unlike traditional threads, coroutines allow you to perform asynchronous tasks without blocking the main thread. This means your app remains responsive, even when handling complex or time-consuming operations. Coroutines are designed to be easy to use and maintain, making them a popular choice for modern Android and server-side development. By leveraging coroutines, you can write non-blocking code that looks and feels like regular, sequential code. In Kotlin, every coroutine is associated with a job. Think of a job as a handle or reference to the coroutine's lifecycle. With a job, you can start, cancel, or check the status of a coroutine at any time. This makes it easier to manage complex asynchronous operations, especially when you have multiple coroutines running simultaneously. The job provides several states that reflect where the coroutine is in its lifecycle, which we'll explore in detail next. The lifecycle of a coroutine's job consists of several distinct states: new, active, completing, completed, canceling, and canceled. Each state represents a different phase in the coroutine's execution. Understanding these states helps you write more predictable and robust asynchronous code. We'll walk through each state, explain how coroutines transition between them, and provide code examples to illustrate these concepts. The new state is where every coroutine begins its journey. At this point, the coroutine is created but hasn't started running yet. This is useful when you want to set up a coroutine and control exactly when it starts. For example, you might create a coroutine and only start it in response to a user action or a specific event in your application. Once a coroutine starts running, it enters the active state. In this phase, the coroutine is executing its assigned tasks. This is where most of the work happens, such as fetching data, processing information, or updating the UI. Monitoring the active state is crucial for understanding when your coroutine is busy and when it's ready for the next step. As a coroutine finishes its work, it transitions into the completing state. This state indicates that the coroutine is wrapping up its tasks and preparing to finish. It's a brief phase, but it's important for ensuring that any final operations, such as saving data or releasing resources, are completed before the coroutine ends. After all tasks are done, the coroutine enters the completed state. This means the coroutine has successfully finished its execution. At this point, you can safely perform any post-processing or notify other parts of your application that the work is done. Monitoring the completed state is helpful for triggering follow-up actions. Sometimes, you need to stop a coroutine before it finishes. When you cancel a coroutine, it enters the canceling state. Here, the coroutine is in the process of being stopped, and any ongoing work should be cleaned up. This is especially important for releasing resources or rolling back changes to avoid leaks or inconsistent states. Once the cancellation process is complete, the coroutine reaches the canceled state. At this point, the coroutine has stopped all execution and will not complete its tasks. This state is useful for confirming that a coroutine has been properly terminated and for handling any necessary post-cancellation logic. To better understand how coroutines move between these states, it helps to visualize the lifecycle as a flow diagram. Each transition, such as starting, completing, or canceling, moves the coroutine from one state to another. This visual approach clarifies the overall process and helps you anticipate how your code will behave in different scenarios. Let's look at a practical example of the new state. When you create a coroutine but haven't started it yet, it remains in the new state. This allows you to prepare the coroutine and control exactly when it should begin, giving you flexibility in managing asynchronous tasks. When a coroutine starts running, it transitions to the active state. Here's an example. You launch a coroutine to perform a task, such as fetching data or processing input. While the coroutine is running, it's considered active. This is the main phase where your asynchronous logic executes. As the coroutine finishes its assigned work, it enters the completing state. This is a short-lived phase where the coroutine wraps up any remaining operations. For example, you might save data or release resources during this state, ensuring everything is finalized before the coroutine ends. Once all tasks are done, the coroutine enters the completed state. In this example, after the coroutine finishes its work, you can check its status and perform any necessary follow-up actions. This is a good time to update the UI or notify other components that the operation is finished. If you need to stop a coroutine before it completes, you can cancel it. The coroutine then enters the canceling state. During this phase, it's important to clean up any resources or handle unfinished work to avoid issues like memory leaks or inconsistent data. After the cancellation process is complete, the coroutine is in the canceled state. At this point, it has stopped all execution and will not finish its tasks. This state is useful for confirming that a coroutine has been properly terminated and for handling any necessary post-cancellation logic. Coroutine scope defines the boundaries within which coroutines can be launched. It helps manage the lifecycle of coroutines and enforces structured concurrency. For example, when a scope is canceled, all coroutines launched within that scope are also canceled. Common scopes include global scope, which lives for the entire application, and user-defined coroutine scope, which can be tied to specific components like activities or fragments. Dispatchers determine which thread or thread pool a coroutine will run on. For example, Dispatchers.Main is used for UI operations, Dispatchers.io is optimized for I/O tasks like network calls, and Dispatchers.Default is for CPU-intensive work. Choosing the right dispatcher affects how your coroutines execute and can impact performance and responsiveness. Managing failures and exceptions is essential for building robust applications. In Kotlin, exceptions thrown in a coroutine are propagated to the parent coroutine by default. If the parent catches the exception, the child coroutine is canceled, and the exception is passed up the hierarchy. This structured approach helps maintain stability and predictability in your code. The supervisor scope function allows you to handle failures of child coroutines independently. If one child coroutine fails, it does not cancel the other child coroutines or the parent. This is especially useful when you want to isolate failures and ensure that one error doesn't bring down the entire operation. CoroutineExceptionHandler is a tool for handling uncaught exceptions at the coroutine level. By passing this handler as part of the coroutine context, you can manage exceptions that aren't caught within the coroutine itself. This ensures that errors are handled gracefully and don't crash your application. When a coroutine fails or is canceled, it's important to clean up any resources, such as closing files or releasing locks. Using a finally block ensures that cleanup code runs regardless of whether an exception occurs. This practice helps prevent resource leaks and keeps your application stable. Launching a coroutine inside another coroutine creates a nested structure. The child coroutine inherits the lifecycle of its parent, meaning if the parent is canceled, the child will also be canceled unless it's launched in a different context. This behavior is important for managing complex asynchronous workflows. Let's see how nested coroutines behave when the parent is canceled. If you cancel the parent coroutine, all its children are also canceled. This ensures that no orphan coroutines are left running, which could lead to unexpected behavior or resource leaks. After a coroutine is canceled, its job transitions to the completed state. This means that even canceled coroutines are considered completed from the perspective of the job. You can check this state to confirm that the coroutine has fully stopped and perform any necessary cleanup. Always launch coroutines within a specific scope to ensure they are tied to the lifecycle of the component that creates them. This approach, known as structured concurrency, helps prevent memory leaks and ensures proper cancellation of coroutines when they're no longer needed. It's recommended to use coroutine scope for managing coroutines tied to specific components, such as activities or fragments. Avoid using global scope unless absolutely necessary, as it can lead to uncontrolled coroutine lifetimes and potential resource issues. Implement exception handling within your coroutines to manage failures gracefully. Use try-catch blocks or coroutine exception handlers to catch and handle exceptions effectively, ensuring your application remains stable even when errors occur. Keep an eye on coroutine states using invoke-on-completion and by checking the status of jobs. This allows you to manage the lifecycle effectively, handle necessary cleanup, and ensure your asynchronous operations are running smoothly. Avoid blocking the coroutine dispatcher with long-running tasks. Instead, use with-context to switch contexts when needed. This keeps your application responsive and ensures that coroutines don't interfere with each other's performance. Understanding the coroutine lifecycle is essential for writing robust and efficient asynchronous code in Kotlin. By mastering coroutine states, handling exceptions, and following best practices like structured concurrency, you can build applications that are both reliable and easy to maintain. Remember to manage parent-child relationships, clean up resources, and always monitor the state of your coroutines for the best results.